As a final example of Bayes' rule, let's look at a case where we can see the impacts of each of these values. So let's use home drug testing as an example. Home drug testing is often billed as being 99% accurate. Now for a given drug test, let's imagine that that has two meanings. All drug tests have these two meanings, but we'll see what these values imply for this particular case. A drug test can be sensitive and or specific. So in our example, we're going to pretend that our home drug test is 99% sensitive. That means if you're a drug user, 99% of the time you will test positive. Specificity has to do with how likely it is to have a positive when it's not a drug user. So 98% specificity means that 98% of the time that a person is a non-user, they will test negative. In contrast, that means 2% will test positive. You'll notice that these are conditional probabilities, which is one of the things we need for Bayesian analysis. Now let's imagine that a random citizen tests positive for this drug. What is the probability that they are actually a drug user? So, if we have 1,000 individuals and 28 test positive, think through how many of those you think are going to be true positives, people who are actually drug users. So for the first 4, think of it this way. Is this next person a drug user or not? Many of you are probably thinking that there's a very high probability of this being the case. But for these first 4, we see the first is a user, a non-user, a non-user, and a non-user. I'm going to show you the math in a second, but I can show you that under certain conditions, in this case, if 1% of the population are actually users, only 1 in 3 positive drug tests are actually drug users. So let's take this a little bit further and imagine we're testing 10,000 individuals. We're going to draw a little table. Okay? So we're going to have positive and negative test results for users and non-drug users. We're going to be interested in those sums. So out of 10,000 people, if 1% are drug users, we're going to have 100 drug users in our sample. If we are 99% sensitive, that's going to be 99 positive tests. If we are 98% specific, that means 2% of our remaining 9,900 are going to test positive, which is 198. This means there are a total of 297 positive drug tests. Given that we're only interested in the outcome of a positive test, because we are interested in the random citizen that tested positive, that means we take 99 divided by 297, which gives us 1 in 3. Now we can fill the table in with the negative results, but importantly, those results don't impact our judgment in this case. In this case, though, we can see that if we get a negative result, we can be far more confident that the person is a non-user than a user. But what if 10% of people are users? Now, in our sample of 10,000 people, instead of having 100 users, we have 1,000. That means that 99% gives us 990 positive tests from users, and because we only have 9,000 non-users, we now only get 180. That means that there's a total of not 297, but a much larger number, and that means that our total probability is 84.6%. This total is important because it shows us that what matters is not just these accuracy measures, but also the overall probability of being a user in the sample. This is especially important for things like medical testing, where a positive cancer screening is much differently interpreted if the base rate is higher or lower. This is something you should keep in mind when you review the results of testing either for drugs or other medical conditions.